Okay, so let me introduce the last homework set. And we certainly did not go through a lot of the book. More than half of the book we didn't cover. But if you deeply understand a few of these algorithms, then the others become very similar. So I hope that you can see that this algorithm here, this GMRES algorithm, is very closely related to the Hessenberg decomposition. So over time you can develop a toolbox of algorithms that you're familiar with. And if you really understand how they work and how they work together, it really helps you to be able to implement and to choose the best one for the right situation. A lot of these algorithms have to do with orthogonality, and you'll see that orthogonality plays an important role in this algorithm also. So this one is called GMRES, this algorithm, and there's a description in the book, and then I'll read this, what I have here. GMRES stands for Generalized Minimum Residual. Now, residual means error. So you're trying to minimize error. All right, so GMRES is an extremely important technique in modern computational mathematics. In enormous modeling problems like weather modeling, it's necessary to find solutions to A equals B for enormous matrices, like 1,000,000 by 1,000,000. Okay, this type of problem is one of the, you can say, holy grails for computation. This is one of the reasons why people are looking forward to quantum computation, because this sort of problem has a lot of parallel operations, and a quantum computer can really do this kind of problem very, very well. Okay. All right, so the reason why this problem is important in weather modeling is because physics is usually described by differential equations, and in the computer, differential equations are coded as matrix equations. So when we get to numerical analysis next year, if you take that next year, you'll see that all that we've talked about matrices really also carries over when you talk about the numerical solution of differential equations. A very, very useful material that we've done. Similarly, modern data science deals with enormous numbers of interrelated variables. Like if you're doing image recognition, you have millions of pixels. And the pixel values may be interrelated. For instance, if you're trying to recognize a cat or a tree, then you have the pixels in your image are somehow related, and your algorithm has to figure out the relationship. So whenever there are lots of interrelated variables, you will probably find a matrix relating pairs of variables. The idea of correlation, I've talked about this before. These systems are too large to be solved even by the fastest computers. It's important to realize that this is always going to be true. So you might say that as computers get more faster and they get more powerful, well, then you won't need these algorithms. Well, that's not true, because when you get a computer that's faster, then people start looking at bigger problems. And I guarantee the problem is always going to be bigger than the computer, because there are problems of unlimited size out there. So no matter how big your computer is, you're always going to need techniques like this where you don't get an exact solution, you get an approximate solution. So this is a sure bet that this material is going to be valuable for centuries and centuries to come. Well, there's not a sure bet on anything, but it's a sure bet than some other things. Okay, so as I said, as you get faster computers, the bigger problems get bigger too. So as long as computers are with us, GMRES will be used. Okay, the point of GMRES is to eliminate large, complicated operations like matrix multiplication and use a limited number of matrix vector multiplications instead. For a 1,000,000 by 1,000,000 matrix vector multiplication takes 1/1,000,000th the computer time for a full matrix multiplication. So you can think about what that means. Multiply a 1,000,000 by 1,000,000 matrix times one vector. How much time does that take? Or multiply a 1,000,000 by 1,000,000 matrix times another 1,000,000 by 1,000,000 matrix. How much time does that take? And you'll see that the time for the first is a lot less than the second. Okay. Now, the point of a GMRES is to choose an auspicious subspace, one that's promising, one that will probably give us a vector that's close to the solution we want, and then use least squares to find the best solution within that subspace. Okay, so if I just draw a picture here, right, suppose I want to find some vector here AX equals B, right? And suppose I know that suppose the vector is out here somewhere, right? Now, if I have some idea what of a subspace that may be close to this vector, for instance, maybe I can construct a subspace that's something like this, right? And here's 0 here, okay? Now, what I would want to do then is I'd want to take the projection here, right? And then this vector, this blue vector, will be close to this purple one, but a lot easier to find. This purple is way out in space somewhere, I don't know where. But if I can localize this smaller subspace and find a solution in this smaller subspace that's close, that may be good enough. Now, when you have lots and lots of dimensions, you probably can do better than this. I can only show 3 dimensions, so you don't see much. The blue doesn't look very close to the purple. But when you get more dimensions, you find that things get better this way, and you can cut down the number of dimensions tremendously. Okay, so for a given matrix A, the best subspace of size k would be the set of k eigenvectors corresponding to the largest eigenvalues. Okay, so this is because an eigenvector v with small eigenvalues gives a small value of AV, so it does not add a large error, right? If I have an eigenvalue of 0.001, right, and then I take A times that eigenvalue, well, that eigenvector, well, then the size of that vector shrinks by 0.001. So adding multiples of that eigenvector to my solution is not going to change the answer very much. Okay, so we don't expect that to play a big role. So we want to look at solutions that consist of linear combinations of eigenvectors with large eigenvalues, because that will get you close. The eigenvectors with small eigenvalues are not going to get you much closer to where you want for your solution. All right. So I'm going to put a colon here because this next problem will illustrate this point. All right, so let's illustrate this point. So given the 3 by 3 matrix A with normalized eigenvectors v1, v2, v3, and eigenvalues lambda 1, lambda 2, lambda 3. Okay. Let's suppose that these 3 eigenvalues are decreasing in order, and the absolute value of lambda 3 is 0.01. Okay. All right. So this is a theoretical problem, but I have it down to just a few numbers, so I think it's still manageable. So suppose the exact solution to AX equals B is X is this linear combination of my 3 eigenvectors. Okay, so I got a linear combination of 3 eigenvectors. That's a solution of this equation. Okay, now let S be the subspace spanned by V1, V2. Those are the first 2 eigenvectors, and these have eigenvalues larger than 0.01. Show that, okay, let U be the vector in S. Okay, vector in S. S is this subspace spanned by 2 vectors. So it's a linear combination of these 2 vectors. Now I want to find this vector that minimizes the norm of this difference, AU minus B. Okay, so it's the best solution for all vectors in S. Okay, it has the smallest possible norm. So of course we want one that has small norm to minimize our error. Okay, so I want to show that this norm, this error, is less than or equal to 0.01 times C3. Okay, of course this 0.01 you can see comes from lambda 3. All right, now be careful. A may not be symmetric, so the eigenvectors may not be orthogonal. But you may proceed by showing there's at least one vector W in S for which AW minus B less than or equal to 0.01 times C3. Okay. Now let's think for a moment what this vector W may look like. Well, can I get a vector in S that's close to X? All right, X is C1v1 plus C2v2 plus C3v3. Okay, but S has to be in the subspace spanned by V1 and V2. All right, so think about a vector that's spanned by V1 and V2 that's going to be close to this X. Right, you can maybe think about how you would modify X to get a vector that's in V1, V2, and then you should take that vector and call that W, and then show that AW minus B has a small error when I do this. All right, so that's kind of the approach you could take for problem 1. All right, let's look at the next one. Okay, so generalize your proof in 1. So I did a simple example here. This is a general statement. Okay, so what you want to do is if you write this well, all you have to do is replace your index 1, 2, 3 with an index up to n. You probably have to introduce summation notation here. Okay, so why don't I just say that? So you will use summation notation. Okay, so given the n by n matrix A with normalized eigenvectors vk and eigenvalues lambda k. Okay, now I need to make sure that I said that these are normalized up here. Yes, these are normalized. Normalized eigenvectors means they have norm 1, right? Remember that. These vectors have norm 1. Okay. All right, so we have normalized eigenvectors and these eigenvalues. Suppose we have lambda 1 greater than or equal to lambda 2, dot, 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 greater than or equal to lambda n. Okay. All right. So suppose the exact solution to ax equals b is this sum up to n of ck vk. Let S be the subspace spanned by v1 through vm minus 1, where m is less than n. So I don't take all the eigenvectors, I just take the first m minus 1 of them. Okay. Let u be the vector in S that minimizes au minus b. So this should look familiar to the previous example. Okay. So, okay. Show that the norm of au minus b is less than or equal to lambda m, the mth eigenvector, times the sum of these coefficients. Okay, these are the coefficients in my original linear combination of x. So in other words, if lambda m is small, then I'm going to get a small error. Okay, the result shows that if the mth eigenvalue is small, then we can find a vector u that's spanned by the first m minus 1 eigenvectors that nearly solves au equals b. All right, now, unfortunately, with a matrix, you can't find the eigenvectors easily. If you find the eigenvectors, then that's an even harder problem than solving ax equals b. So you want to avoid that. So you want to find a subspace that approximates the space spanned by the largest eigenvectors. Okay, so we're going to use Hessenberg. Okay, question 3. Let q1 through qn be the vectors generated by the Hessenberg process, starting with the vector b. Now, if you look on page 116, you see that q1 is the vector b divided by the norm of b. That's how you define the first vector in this orthogonal sequence of vectors. So I'll these are orthogonal, right? Right? Just to make clear that we understand that. Okay, we therefore have equation 3 on page 116. Okay, so you can look at equation 3 on page 116. Equation 3 on page 116, let me turn there. This is a matrix equation relating the matrix A to the Hessenberg matrix, and that last matrix on the right side of 3 is H k plus 1 comma k. Okay, all right, so he writes this as AQK equals QK plus 1 HK plus 1K. You can look on page 116 and see how it's written there at the bottom of the page. All right. Where am I? Let's see. All right, so we have this. Okay, we are seeking coefficients y1 through ym, where m is less than or equal to n, such that this linear combination is nearly a solution to au equals b. So it's the same setup as what we talked about above. In other words, we want to find coefficients y1 through ym such that a times this linear combination of my q vectors minus b, minus the vector b, is minimized. So if I plug this vector in, if I plug this linear combination vector in for x, then it's nearly a solution to ax equals b, because ax minus b has a small norm. Okay. Now, show that the expression a times this expression, this linear combination minus b, can be rewritten this way in terms of these matrices. Qm plus 1, that's the matrix that has m plus 1 columns, and the m plus 1 columns are the first m plus 1 of these orthogonal vectors. Okay, hm plus 1m, that's defined in the chapter. All right, so you can use the equation in the chapter that involves hm plus 1m. Okay, and then you write this minus norm of b times q1. Okay, so I can rewrite this expression here. I want to show that this expression here is equal to this expression here. So this kind of simplifies things and puts things in terms of the q matrices. And this vector y is a column vector with m components. So I take the coefficients y and I form them into a column vector. Okay. All right, question 4. Show that this expression is orthogonal to Q1 if and only if HMY minus BE1 is orthogonal to E1, where E1 is the first standard basis vector in Rm. Okay. For instance, E1 in R3 is 1, 0, 0. Okay. So we've talked about standard basis vectors before. Okay. So this is kind of the first step in a more general statement that I'm working up to, but this one should be, I mean, you can see how it works by using orthogonality. Remember, these columns are orthogonal vectors, n plus 1 orthogonal vectors. This Q1 is actually the same as the first column here. All right? Okay. Now, the way to do this, I'll give you a hint here, is you can take this expression here and multiply it on the left. Like I should say this, on the left. Whoops, where'd I go? Sorry. Where are we? Multiplying on the left, where'd I go? Here we go. On the left. Okay. And then and then you should compute what this is. Okay. And see how you can get this expression here, HMY minus BE1, by doing this operation. Okay. All right. So I just point out that this here is a much simpler and much smaller, could be much smaller matrix than my original, because if little m is much smaller than big N, I'm sorry, if big M is much smaller than big N, then this Q has n rows, right? But this has only m rows. E1 only has m entries. So I've cut my number of entries down by a factor of from n. I've cut it down to m. Okay. So in other words, if I have a 1,000 by 1,000 matrix, but I only take 3, 4 vectors, I'm going to decrease my computation by a factor of like 300. Okay, so that's the thing. Take this here, multiply both sides, multiply this on the left by Q1 transpose, and ensure that gives you something here. All right, So problem 5 is a generalization of that. Instead of using Q1, use QJ. Okay. All right. So I think this is correct. Okay. So that's a generalization. All right. Now, suppose y is the least square solution to this here. So let me say, okay, so I'll just say here, recall that for a least square solution, the error is orthogonal to the columns of HM. All right. So we did some exercises like that. Remember that orthogonal error is minimized error. Just to, again, draw this same old picture. If I have a plane, same old picture, same old intuition, always the same. Boring mathematics, always the same. All right. You've got some plane here, right? And I got some vector outside of the plane, which is here. So I started, so this is 0, okay? Now, where's the vector in the plane that minimizes the distance? Well, it's that old, it says your old projection, right? You project down here, and then this vector here is the one that minimizes, right? This vector here is the one that minimizes. Your error is here. Your error is perpendicular to your solution. It's perpendicular to the columns that span this space. The columns of H are the linear combination of vectors that you're using to get this vector. So the error is orthogonal to the columns of HM. Okay. right, now, so how you can use this solution here, the solution y to this equation, to obtain the least square solution of ax equals b. Ax equals b was the original solution with the large vectors and with more of them. Okay, but in this case, x is restricted to the subspace spanned by these here. So in other words, i.e., the error is orthogonal to, it has to be orthogonal to these vectors. All right? Okay. Okay, so now I want to relate this to the stuff we talked about eigenvectors before. We've shown in a previous assignment that all these vectors do not exactly span the space of k leading eigenvectors. They do approximate this space. And the reason is, as you take k powers, the leading eigenvectors are starting to get more and more important. And the smaller eigenvectors, eigenvectors with small eigenvalues get less and less important. They kind of damp out very quickly until all you have here are linear combinations of your biggest eigenvectors. All right, so I cooked up this matrix here, which you can go ahead and put in. And I define the vector b as b equals ax, where x is 1, 1, 1, 1. Okay, so you can compute this using Python. Okay. Okay. All right, so using the vector b as a starting vector, the Hessenberg decomposition for a is this. So I actually did this. You can check with your own Hessenberg program. I thought if you were having trouble with your Hessenberg, I'd save you time by doing this. So these are the orthogonal vectors in Qn, and this h is the Hessenberg. And notice that this Hessenberg has the form. Here's 0, 0, 0. We have zeros below here. And we've got these entries here. So this may take you a little while. You can probably copy and paste this into your Jupyter if you want to use this. But you'll have to call this an array, and you'll have to call this an array. Okay, so here I'll just say that just to make it easier. This is array, or np.array, depending on how you do it. And then this one is also going to be array. All right. All right, now. All right, so using the above, find the least square solution to b equals ax, where x is restricted to the subspace q1, q2. All right, so when I say using the above, I want you to use actually, there is no problem 7 here. So I should make this problem 7 because I didn't ask you anything here. So this is problem 7. So using problems, I should say using problem 6. Okay, problem 6 tells you, it gives you a relationship between this least square solution and this least square solution. Okay. Okay. So you should be able to solve this least square solution to get this least square solution, and that's what I'm asking you to do for this specific matrix. All right. Okay. Okay. Okay, so then calculate the error. So then calculate this error. Once you've computed this x and you have b, let's see. Then you can compute this error. Okay. Okay, problem 8. Find the least square solution to b equals ax, where x is restricted to the subspace q1, q2, q3. Okay, so this one had q1, q2, this one has q1, q2, q3. So it's going to be very similar. Just add one more vector. Okay. And then here you can just use a method online, calculate whatever you want to compute the eigenvalues of A and relate the result that you get here to the results you saw in these two parts here, in 7 and 8. Okay. All right, so that's the assignment. And please feel free to ask me questions on Hangouts or email, however you like.